We also already discussed, no, the undamped free vibration system, and also the case 2B, the underdamped critical, the underdamped free vibration response system. So, again, no, just to reiterate that our auxiliary equation, if you remember our auxiliary equation, so we have an equation of motion, di ba, nga, ito, mu double dot of t plus c u dot of t plus k u of t times u of t is equal to 0. Its auxiliary equation is in the form s squared plus c over m s plus k over m is equal to 0, or s squared plus c over m times s plus omega squared is equal to 0. So the roots of these auxiliary equations to ang equation of motion has three distinct roots. First, we have 2a, and when c over 2m, its determinants, no, c over 2m squared minus omega squared is greater than 0. Its second case is when roots, or sorry, the determinant c over 2m squared minus omega squared is less than 0. And 2c, when c over 2m, quantity c over 2m squared minus omega squared is equal to 0. So first, na to discuss last time, we have this case 2b. This is the underdamped free vibration system, or the underdamped system. So now here we'll be discussing 2c. When c over 2m squared minus omega squared is equal to 0. So this is a critical damp system. So recall, no, diba, that the roots of the, what we call here, the of the auxiliary equation, s is equal to negative c over 2m plus or minus the square root of c over 2m squared minus omega squared. Now, when in a critical damp system, so we have a condition. This is the case 2c, when c over 2m squared minus omega squared is equal to 0. And then if we transpose omega squared, we will have this equation. And then if we extract the roots of both sides, we will arrive that c over 2m is equal to omega. And our damping coefficient is equal to 2m omega. So in this condition, when our determinant is equal to 0, it means that our coefficient of damping is equal to 2m omega, which is equal to the coefficient of the critical damping. So in this situation where the our damping and then the critical damping is equal, our xi, or our damping factor, which is the ratio of the damping over the critical damping, will be equal to 1. And then our root s, so if we just substitute the values of c, so we have s is equal to negative c, and then our c is 2m omega over 2m plus or minus the square root of. And we know that the square root of our determinant is just a 0. We just cancel out this 2m, and then eventually we'll come up with the solution that s, or the root of our auxiliary equation, is equal to negative omega. So what will happen is that we go back again to a general equation of or solution, but this time, since the roots of the auxiliary equation is 1 and real, so dili na tayo na magamit atong ut is equal to g1 e to the s1t plus g2 e to the s2t. So our s here is just equal. So that's why there is just s here. There is no s1 and s2. But if you notice, na added T diri. So actually, no, this is a derived solution for a roots, no, for if our roots, no, di ba supposedly we have S1 and S2. If the S1 and S2 or the roots 1 and 2 are the same and equal, then actually taas na siya solution, di ba? Atong gingon earlier when we have two unknowns, we should have also two equations. Since ang atong roots is the same, so mangitatag another way or pamaagi to get the second equation in order to arrive at our particular answer. So, taas na ito nga solution, we just come up with this one that the u of t is equal to g1 e to the st plus t g to e to the st. And since we have our common term here, the e to the st, and then we substitute the value of s, which is the negative omega, then we will arrive with this equation. So, muna siya yung gingon nila no, the second term must contain t since the two roots of the quadratic equation in S are identical. So, prayer good na ano, if your roots are ingana, then you will have that t equal to e1 e to the negative whatever you have alpha t plus t c2 e to the negative alpha t, which is this is just a summarized formula na no, wala na nato na siya gi tagsa-tagsa og show why we arrive in this formula or equation. So after no nga makuha na to si u of t, so of course kuha na to si u dot of t as part of our initial condition. And if we differentiate this equation here, we will arrive with this equation u dot of t is equal to negative omega times quantity g1 plus t g2 times e to the negative omega t plus g2 e to the negative omega t. So using the initial condition, so we try to use the initial conditions, we can solve the constants g1 and g2. And upon solving the constants g1 and g2, we can substitute the value of this in our equation of motion. So this time, line about the equation of motion, this is the general solution. So if you notice now, our equation of motion is in the form u of t is equal to quantity u0 times quantity 1 plus omega t plus u dot 0 t times e to the negative omega t. If you try to look the formula, there is no cosine function nor a sine function. So if you remember, no, if we graph the time versus the displacement, kung nakakuha na siya sine or cosine function, it is expected that the graph is cyclic or sinusoidal, we call this sinusoidal, or there is an oscillation or harmonic uh, oscillation or motion. But if you look with this one, no, there is no motion. So when you graph that, let's say you have an initial displacement, eventually it will look this way. It will eventually come to rest without oscillation or oscillating. So this is a critical damp system. This happens when the damping factor of your structure is just equal to 1. So the moment that you apply the force, dili na siya mo cycle nga mo, ala pa siya mo vibrate pa si structure. Dili na siya back and forth motion until it will come to rest. But in a critical damp system, the moment you applied the force or the displacement, it will come back to its original position without oscillation. So this happens when you're damping critical, when your damping is equal to the critical damping and your damping factor is equal to 1. So muna siya may tabo. So muna siya no, this is a critical damp system. There is no oscillation. So imumasahan din the no oscillations. The critical damping just eliminated them. So here we have a graph. Katong gingon ako ninyo time versus displacement. if we have an initial displacement here, and then since our coefficient of damping is equal to the critical damping 2m omega, therefore there is no oscillation when there is an applied displacement. It will just go back to its original position and then throughout the time. So there is no oscillation sa ato ang structure nga nahitabo. This is case 2C. Now, another, we have case 2A, di ba? Si 2A, ang iyang determinant C over 2m, quantity C over 2m squared minus omega squared is greater than 0. So we will have C over 2m. So we will have an inequality like this, omega squared, and then if we start to square out the both sides, we will have C over 2m is greater than omega squared, or the damping is greater, there's no grade is greater than the 2m omega. So in this case 2A, we call that an overdamped system. When our damping is greater than the critical damping. So it is not encountered in practice, and there is no oscillations that happens in an overdamped system. So mo ni siya pag overdamped. So here we have a graph of the time over the natural vibration period versus the displacement at time t over initial displacement. So kung makita no, there is a sinusoidal graph, taas ang amplitude, and then eventually through time nagkagamay, and then this will eventually come to rest. This one here kaning starting from a high amplitude, and then there is an oscillation obviously with this graph. This is under damped or system. This reflects reality. Now, if the system is critically damped, so there will be no oscillation nga mahitabo sa tuang structure. So what will happen upon the displacement? It will go back to its original position. So kani si critical damping is the boundary for underdamping and overdamping. Since it is the boundary of underdamping and overdamping, it then shows that conditional graph is underdamped, and then this damp is, we call that the overdamp. So the critically damp has a damping factor equal to 1, and an overdamp will have a factor or damping factor greater than 1. So here we have a damping factor of 2, or it might be 5, or it will be 10. Now, in reality, this structure doesn't really exist. So, ang pinaka-realistic na diri nga representation sa structure is we have the case 2B. When the structure is so if we apply displacement on a structure, it will oscillate and eventually it will come to rest. So sa structure no, it is impossible to have an overdamped one. Di kita makakita na. Though in things lugar no, in sa lalay nga butang, let's say not the structure, there are things na kuan na siya damping. The damping is really observed. For instance, here, I want to show you a video of damping. So, para mas ma-appreciate ninyo. So here, nasa a ball, and then if you release that ball, di ba si ball is muuntol gid siya, and then until it will reach to a point nga mo stop siya. So if you notice no, na ang upon releasing, there is an energy, and then there is an oscillation like that one, and then so naghinay ang paguntol ni sa bola until it came to rest. Now there is a second ball, na niunto lang siya gamay, and then niundang na dahil siya pag untol. So that second ball, it has a larger damping coefficient compared to the first ball. So muna siya si damping. If the material has a damping, it absorbs the energy and goes back to its original position for a shorter period of time. So that is no the discussion on the free vibration system. So we have a structure initially undamped, and then we try to analyze its motion, and its oscillation is perpetual, forever and ever, and then its motion is harmonic, and it doesn't stop, and the amplitude through time is just the same. Now we try to include damping in our structure. So mo nitong we have three cases. We have the underdamp, we have the critically damp, and then the overdamp. So kani siya kada cases, no, kada cases sa ato ang motion, the equation of motion is different. There is a specific equation of motion for each type of system, no, kung sa iyang behavior. For the underdamp, we have different equation of motion, but the process, though they have different equation, the process is almost very similar. No, from a differential equation, we try to get its all auxiliary equations, and then afterwards, we try to establish our initial conditions, and then try to solve it algebraically. So we eliminate the terms to solve the constants G1 and then the G2. Then eventually, maabot din sa point where we have our equation of motion, and then we apply the concept of amplitude, the period, and the natural frequency of our structure. And then, so we have the underdamp. So underdamp is the real or the realistic representation of our structures, where when the structure is displaced, no, there is an oscillation. What will happen is that it will oscillate through time until, but of course, magagamay ang displacement until it will come to rest. So the critically damped and the overdamped, so mo to siya ang there is no oscillation, and upon application of the displacement or there is a displacement or deformation, the structure will eventually return to its original position.